Okay, so we are very happy today to have Professor David Reutter. So he is a mathematician leading the Homotopy research group at the University of Hamburg, where he investigates topological quantum field theory beyond 3 dimensions. His research focuses on higher category theory, low-dimensional topology, homotopy theory, and quantum algebra, particularly in relation to fusion category and TQFT. After earning his PhD at Oxford under Jamie Vicary, he held postdoctoral position at the Max Planck Institute for Mathematical and MSRI. He is known for his contribution to fusion to categories, semi-simple 4D TQFTs, and the categorification of algebraic structure. David, please, you can start.
Thank you. All right, thanks for the introduction, and it's very nice to speak here online. What I was planning to talk about is a project that's ongoing work with Theo Johnson-Fried. The first paper on this should appear soon, hopefully. We are sort of in the final stages. And the title of this talk was, okay, I should use the marker, not the eraser. The title of this talk is Homotopy Quantum Groups. And the idea is, well, I'll get to the idea, but the idea is to assign groups as invariants to topological quantum field theories in high dimensions. And show that sort of the classification of topological field theories in high dimensions becomes easier than the classification of topological field theories in 3 and 4 dimensions, just like the classification of manifolds up to diffeomorphism becomes simpler by surgery theory. And sort of these ideas are closely related, and this whole program can be seen as a sort of dual to surgery theory. But I try to sort of stay fairly basic and work with 1 and sometimes 2 categories, and only in the end I'll touch upon higher categories a little bit. Okay, let's get going. So, our class of topological quantum field theories that are very important in physics and in mathematics are the so-called finite sigma models or finite path integrals or Dijkgraaf-Witten theories. They have sort of lots of names. The idea always is you take a topological space, which is pi finite, sometimes just called finite, better term is called as pi finite. Pi finite just means that all its homotopy groups are finite, and there are only finitely many homotopy groups that are non-zero. Oh, by the way, I should say, if you have any questions or comments or anything along these lines, please just shout in and let's make this interactive. All right, so if you have such a space, you can always construct a TQFT of any dimension. I'll always talk here about d+1 dimensional TQFTs. That's sort of the dimension shift that's easy for this talk. But D is arbitrary. And what it does, it assigns to a closed D manifold just the linearization of the space of maps from this D manifold sigma to X. And to a D+1 dimension manifold, if it's closed, it just sums over maps. So it's a certain weighted sum of sort of a certain count of the space of maps from M to X. You sum over pi 0 of the space. So when I write sum over F, what I really mean is sum over pi 0 from maps from M to X. And you weight this by a certain factor. This is a so-called homotopy cardinality. So this is defined in some particular way. It knows about the homotopy groups of these automorphism spaces. But this doesn't really matter. The point is you can write down a d+1 dimensional TQFT in all dimensions. And a well-known example of this is if you take X to just be the classifying space of a finite group G. So if you want to think of a topological space just as a higher groupoid, this is just the one groupoid with a single object and automorphisms G, this finite group, then this construction produces for you what's known as Dijkgraaf-Witten gauge theory. But you can also do this for other spaces. For example, you could take an abelian group and shift it into degree R. So this is a space with only homotopy in degree R being the abelian group A, and otherwise it's 0. And then you get something that in physics is known as R-form gauge theory. And you can do a version of this construction where you twist by certain structures and sort of can use coefficients here. So you can sort of beef this up a lot. But this is sort of the basic idea. This is sort of a very important class of topological quantum field theories. That's sort of indicative of how topological quantum field theories work in general. maybe as a little side comment, this is sort of if you care about full-blown quantum field theories without going into what the definition is, you can look at general sigma models, and this is sort of the topological version of a sigma model. General sigma models being quantum field theories that essentially count maps, but not just homotopy types of maps, but general maps, say smooth maps or maps of Riemannian manifolds, to some target space. And again, there's the same sort of phenomenon happening, that if you want to understand qualitatively how quantum field theories work, it's very important and very indicative to understand how sigma models work. This is sort of here the same. Okay, and so one thing you could ask, for example, is how much does this TQFT remember about the space X? So can it happen that I have two spaces X and Y that are not homotopy equivalent? So first of all, it just sees the homotopy type of the space X, it just sees it up to homotopy. But it can even happen that you have two spaces X and Y that are not homotopy equivalent, yet their sigma models are isomorphic. So roughly what will happen in a sigma model is that it mixes homotopy in degree K with homotopy in degree D minus K. So it sort of folds my space in half, which is essentially an effect of Poincare duality on manifolds on this side. So this is sort of, okay, somewhat unfortunate. You can't recover your space from the TQFT. And these are, of course, very important. This is sort of the topological quantum field theories version of dualities. And of course, again, in quantum field theory, we have similar phenomena. These various dualities go by various names, and this is in some sense the easiest type of duality. But something that happens is that if my spaces are not homotopy equivalent, well, okay, something that happens is the following. These sigma models are not just D plus one dimensional TQFTs. They all have a canonical boundary theory. And the reason they have a canonical boundary theory, you can define it fairly easily, which is just the observation you can make that this formula here, these expressions, nowhere do I need for the right-hand side that my manifold sigma or my manifold M is a closed manifold. So for example, I can just define this for a manifold with boundary sigma and just write down the same expression. And this means what I really have to find is a topological field theory with a boundary theory. So on a manifold sigma with boundary, sort of in the bulk, I assign my D plus one dimensional TQFT, and on the boundary, I do something else. And what I do is still determined by these same formulas. So you should think of a topological space giving rise to a D plus one dimensional topological quantum field theory together with a preferred boundary condition. And this is known as the Neumann boundary condition. Just to recap, in PDEs, the Dirichlet boundary condition is the one where you force the value on the boundary, sort of the position value on the boundary, and the Neumann one is where you force the derivative on the boundary to be something. But since we talk about topological quantum field theories, there are no derivatives, so you just leave the boundary condition open, and that's what happens here. You just use this maps from sigma to X, no restriction on the maps at all, what they do on the boundary, nothing. So this is the Neumann condition in a topological world. And this is a canonical boundary theory. And the key point is that if you look at one of these dualities will in general permute the boundary theories. So if you think of a space as assigning to you a package of a D plus one dimensional TQFT together with the boundary theory, and you remember the boundary theory, then there's a good chance that this recovers the space. Because the sort of dualities we know, they switch the bulk theories, the D plus one dimensional theories, but they will mess up the boundary theories when doing that. And indeed, if X has trivial high homotopy groups, then you can recover the space X from this pair, as long as you interpret TQFT in a good way. So you have to interpret it in a fully extended way to get this statement out. But at least at the sort of heuristic introductory level, this is what you should think. You should think that you can recover the space X from the pair of a sigma model and its boundary theory. Okay, so these are sort of these two pieces of information you know about X. And the slogan you should then develop, and the slogan that we sort of follow in this talk, is that you can think or should think of a pair of an arbitrary TQFT, it doesn't need to be a sigma model, together with a boundary theory as some sort of generalized space. And that is very useful to, if I hand you a TQFT with a boundary theory, it's very useful to think of this as if it would come from a sigma model, even if it doesn't actually. And you can sort of pretend you come from a sigma model and then sort of do the things you would usually do to spaces, and see where this is going. And this is what we will do in a second, where we will try to study the homotopy groups of such a pair. Okay, so this is the slogan here: is a pair of a TQFT with a boundary theory behaves very much like a topological space in some generalized way. And you should try to develop homotopy theory for these guys. Okay. Now, this is only, of course, interesting if you say, oh, I do care about these tuples of a TQFT together with a boundary theory. And I want to argue from two perspectives why such pairs are interesting and important in quantum algebra and quantum symmetries, even if they do not arise from topological spaces. And the first is the so-called SymTFT paradigm. And is the SymTFT paradigm I wrote here after Friedman and Teleman. This is sort of the formulation of Friedman and Teleman. I think the paradigm itself is much older in physics. But the idea is that if I have an arbitrary d-dimensional quantum field theory, so no T here, then it has classical symmetries. It might have a symmetry group, sort of global classical symmetries, not gauge symmetries. And the idea is that these should be generalized, and you should allow, as symmetries of a d-dimensional QFT, a pair of a d plus one-dimensional topological quantum field theory together with a d-dimensional topological boundary theory. So this is sort of the key idea. And these are called quiches, therefore the picture here. Okay, so if I hand you such a pair, you can think of this as the algebraic data or the geometric data, however you want to treat a TQFT, that encapsulates the symmetries of a d-dimensional QFT. And if I hand you a d-dimensional QFT, you should in principle be able to write down such a pair, and it sort of describes the symmetry information. And only if this pair arises from a topological space is this a classical symmetry, and otherwise it's sort of a quantum version of a symmetry. Okay. And I think all of you here in the seminar do know examples of such pairs that are exotic, that are quantum, that go beyond this construction. And namely, sort of the key thing, the key ingredient that gives rise to such a pair in my mind is fusion categories and higher fusion categories. So let me remind you how this works. And these are sort of, if you want, non-homotopical or non-space-like versions of such quantum spaces, right? I think of this, such a pair I call a quantum space for this talk. For example, if I have a fusion 1 category, an ordinary sort of very finite fusion 1 category as we know it, then I think most of you will be familiar with this construction called Turaya-Vero that gives rise to a three-dimensional topological quantum field theory. And this Turaya-Vero theory has a canonical preferred boundary theory. And so indeed, a fusion 1 category gives rise to sort of one of these packages, one of these quantum spaces where the bulk theory is three-dimensional and the boundary theory is two-dimensional. And you can go in one dimension higher, there you need more monodality. So you could start with a braided fusion 1 category. And this again gives rise to a four-dimensional topological quantum field theory. This is often called the Crane-Jeter, or sort of was originally constructed by Crane and Jeter. And this Crane-Jeter theory has a three-dimensional boundary theory, which is known as the Reshetikhin-Turayev TQFT. Okay, so braided fusion 1 categories give you one of these packages in dimensions 4 and 3. And this can be generalized to fusion 2 categories. So every braided, I will say later what a fusion 2 category is. For now, it's not that important. The point is that every braided fusion 1 category gives you an example of a fusion 2 category, and the category of braided fusion 1 category sits fully faithfully inside the category of fusion 2 category. So this construction just generalizes to these gadgets. And then you can continue like this, and sort of it then starts to look more parallel, right? Your fusion 1 categories gives you 3, 2, and fusion 2 categories gives you 4, 3. And braided fusion 1 categories happen to be a special case of that construction for fusion 2 categories. And you can generalize this. And if you start with fusion n categories, I'll say later what those are. You get an n plus 2-dimensional TQFT and an n plus 1-dimensional boundary theory. Right, and inside of this world, there sit braided fusion 1 category. Let me write with it. Sort of inside here, if you like, there are things called braided fusion 1 n minus 1 categories. And inside here, you can sort of make it smaller. There's something called maybe a syleptic fusion in -2 category and so on. And then you can sort of look at more and more special cases of this construction. But if you go sort of up here, it becomes more general. Okay. All right. So that's the picture. This is a fusion n category is an algebraic datum that gives rise to such a quantum space. And as before, by the way, before I was saying a topological space, for example, X gives rise to such a gadget. And then there was a question, can I recover the space X? And now again, at least at this heuristic level here of this talk, if I interpret this correctly in the correct higher category, fully extended and so on, then from this data, you can actually recover the fusion n category up to monoidal equivalence. So you can recover the fusion n category up to monoidal equivalence, physically speaking, as the category of boundary operators. So as the category of, if you want, defects and higher defects that live in the boundary theory. And there is a mathematical way of doing this, and I won't talk about this here. But for example, in 3D, 2D, you really see this, right? This is a bulk three-dimensional TFT with a two-dimensional boundary theory. And you can now ask, what are the line defects or what are the line operators that live in this 2D theory? And these are the objects of my fusion 1 category. These are really lines that live in 2D. So you can sort of draw string diagrams for them, and then you really see your fusion 1 category coming out of that. Okay. Any questions up to this point?
No, it's okay.
Sorry, I didn't get that.
I say it's okay. It's okay. You can.
Okay, so these are examples. So higher fusion categories, fusion 1 categories, fusion 2 categories, and so on, give rise to these packages, these pairs of a TFT and a boundary theory. You know, variously called quiche, or maybe quantum space. Okay, but I was saying earlier that you want to pretend such a pair of a d plus 1 dimensional TFT and a d-dimensional boundary theory behaves like a topological space or generalized topological spaces. And now here is a very basic thing you can do with a topological space. Sort of, if you want to develop homotopy theory, probably historically the first thing you want to do is write down the homotopy groups. Namely, the most basic invariance of this space is it's a fundamental group or fundamental groupoid, really, if the space is not connected. And it's higher homotopy on these abelian groups, pi and x, and for 2, 3, and so on and so forth. Really, of course, when I write it like this, you should remember the higher homotopy groups depend on a choice of base point. And the best, most coherent way to encapsulate this dependence is to think of pi n of x as a functor from the fundamental groupoid to abelian groups, right? It sends any base point as an object in here to an abelian group, pi n x at x. And then it actually also encapsulates the action of the automorphism, so the fundamental group pi 1x at this base point acts on pi nx at this base point. And this sort of all this information is best encoded in such a functor, and such functors are also known as local systems. Okay. So this is later what we're sort of trying to aim for as such a gadget. Okay. And I just write it as pi nx and pretend I don't care about base points, but really when I write pi nx, I really don't think of it just as an abelian group, but as one of these families of abelian groups. Okay. Right, and I was sort of making this point a lot and beating on this point, which is that a d-dimensional quantum space, for me now for this talk, is a pair of a d plus 1 dimensional TGFT and the boundary theory. Okay, and so I won't subscribe to this definition for always and ever, but I think for this talk, it's just a very good intuition for what I'm going to do. And so let's sort of keep this in mind and use that terminology for the next hour or so. And so let's try to define this. So I've sort of, so far, I've, just sort of vaguely referred to what a TGFT and a boundary theory is. Let me be more precise just for the things that I need today and for this presentation. Let me actually define what I mean by this to sort of move into mathematics. And what I mean for this talk and for everything I'm going to say today, that's not what I mean in general, but that's what I mean today, is it's a so-called once extended, open closed frame, not necessarily compact, d plus one dimensional TTFT. So what I mean by that, it's a functor that's defined on a once extended Borderson category. So it's defined on a Borderson category where you have objects are d minus one manifolds, morphisms are d-dimensional Bordersons between them, and two morphisms are d plus one dimensional Bordersons between these Bordersons. Open closed means I do allow manifolds with boundaries for the objects and everywhere. So I'm sort of just allowing these open boundaries. Then it's framed, okay, you can sort of give it an orientation and things you like, but for this talk, every manifold will have a framing, so trivialization of its tangent bundle. And then this is a bit subtle. What this compact means is that, I mean, if you just like sort of the standard definition of TFT, you probably wouldn't care about this at all and just be happy with what I've written up to here. In physics, you often like to consider TFTs that are not defined on all top-dimensional Bordersons. This allows sort of less finite constructions. And compact means in physics language that the TFT is really defined on all manifolds. And not necessarily compact means a TFT that's only defined on top-dimensional Borderson whose outgoing boundary is non-empty. And everything I'm going to say here, in fact, applies to these less finite TFTs. But if you like fusion categories and so on, these are all compact TFTs. So these are really defined on all manifolds. But we sort of took some care in this project to really allow for fairly general constructions. And this is sort of encapsulated by using that definition for d-dimensional quantum space. It's sort of, you don't have to ask it to be fully extended. You don't have to ask it to be defined on all manifolds and so on, just to sort of get us a bit more generality, allow non-semi-simple constructions and the like. But if you do like fusion higher categories, then you can just drop all of this, and this is a fully extended open-closed theory that you have. Okay. There's open closeness. This is what encapsulates that you have a TFT and a boundary theory. Okay, questions on that definition and terminology, really?
It's okay. It's okay.
Okay. And now let me sort of just preview the theorem that we've proven. If you're in dimensions d greater or equal to 4, so there the bulk theory is 5-dimensional and the boundary theory is 4-dimensional or higher. And you have one of these gadgets, one of these d-dimensional quantum spaces, so a 5-dimensional bulk theory and a 4-dimensional boundary theory or higher, which you assume is compact in this sense, so it's defined on all Bordersons whatsoever. And it's superlinear, i.e., as a once extended theory, it's valued in superlinear categories, so module categories over super vector spaces, and compatible functors between these. Then it follows that there is a finite groupoid you could call pi smaller equal to 1q, the fundamental groupoid of this quantum space, and that there are actual finite abelian groups pi k x with this action of pi 1. And these groups generalize the classical homotopy groups when Q is a sigma model. So up to this point, it's all, well, okay, these sort of pairs of a bulk theory and a boundary theory behave a bit like a topological space. And now we're really concrete and saying, look, if you're in high enough dimension, you can actually recover fundamental groupoids and homotopy groups from such a gadget. We're not saying you can recover a space. And I think we have examples. I'd have to go back and think about this. But I want to claim that we have examples which do not come from a space. We do have examples that do not come from a space. Yet you can recover these groups. Okay. And an example of such a d-dimensional quantum space which satisfies this condition 1 and 2 is any higher fusion category in the sort of correct dimensions to be in dimensions 4 and 5. So you do extract these homotopy groups, even if your quantum space, even if your TTFT is built from some higher fusion category, which a priori could be an exotic gadget. So this is, to have these conditions met, you have to go into dimension, you have to talk about fusion 3 categories or higher. I should say, now you could sort of, if you care about fusion 1 categories and braided fusion 1 categories, then it's sort of unfortunate, right? Because I start exactly in the dimension in which I'm sort of just beyond braided fusion categories. Namely, right, the dimension which would have braided fusion categories, where braided fusion 1 categories would give examples, is the dimension d equals 3, where I have a 4-dimensional bulk theory and a 3-dimensional boundary theory. And here is sort of just 1 dimension higher, where you get these groups out. And in d equals 3, what you get out instead, and the same constructions still work, but you won't see groups appearing. You will see Hopf algebras in a certain symmetric or braided. In d equals 3, it will live in some braided category. And these abelian groups will be Hopf algebras rather than abelian groups. So you get sort of generalizations of groups, if you like. But that's sort of also supposed to be the point, that these things work better in higher dimensions. Again, as I said earlier, which is sort of very analogous to how search array theory works better in higher dimensions, and things like the H-coordinate theorem work in higher dimensions, which allow you to classify higher dimensional manifolds much more easily, and it aligns much better with homotopy theory than in low dimensions. And it's sort of the same phenomenon appearing here, that TTFTs in high dimensions behave much more like spaces. Okay. Questions? All right. Then the goal of the talk is to sort of just outline very roughly how you get to this, how you define these groups and these abelian groups. So let's start with the fundamental groupoid, with this finite groupoid pi smaller equal to 1q. So suppose I have one of these d-dimensional quantum spaces. So I remind what this means. It means I have a d+1 dimensional bulk theory and a d-dimensional boundary theory in high dimensions, d equal to 4. And I ask this theory to be once extended, so I will get numbers to every d+1 manifold with a d-dimensional boundary. I get vector spaces to every d manifold with a d-1 dimensional boundary, and I get categories to every d-1 manifold with a d-2 dimensional boundary. And such a d-1 manifold with a d-2 dimensional boundary is the disk. So let's look at the d-1 dimensional disk. And Q, if I evaluate Q on this d-1 dimensional disk, meaning, right, I use the bulk theory in the bulk of the disk, and I use the boundary theory on the boundary of the disk, I do get some category just by dimension counting. And it turns out, as I think most of you will know or have seen, is that this category is symmetric monoidal. Namely, I can use the pair of pans, and the pair of pans gives me a Bordesson from 2 disks to a single disk. So this is a solid pair of pans. And now, depending on the dimension of the disk, if the disk is 2-dimensional, so if d is equal to 3, so that 3 minus 1 is 2, then this is a braided structure that you will get, right? Because you talk about 2 disks moving in a larger 2 disk. If d is equal to 2, then this is a 1 disk. You talk about 2 1 disks moving in a larger 1 disk. This is a monoidal structure. And in higher d, you would get something like an ED structure. But since our target is just a 2 category, this would just be a symmetric monoidal category. Okay, so this category is some symmetric monoidal category. Great. So now we've extracted as sort of our first invariant of our quantum space a symmetric monoidal category. And let's just think about what this category is. If Q arises from some higher fusion symmetry, then what Q of this disk is if you sort of like physics, it's the category of line operators in my higher fusion category. It's essentially the one category you get by just taking the endomorphisms of the identity of the identity of the identity until you sort of end up with just a 1 category. So if you're in a fusion 1 category, so in the case d equals 2, this will just be the fusion 1 category you've started with. If you start with a braided monoidal 1 category, this will just be the braided monoidal 1 category you started with. If you start with a fusion 2 category, this is the same dimension d equals 3, what you then get is you drop the objects. You forget about the objects in the fusion 2 category, and you just remember the endomorphisms of the unit. So you just remember the lines in that fusion 2 category. And in higher dimensions, sort of I haven't yet told you what a fusion n category is, but it is in particular a monoidal n category. And so this is lots of objects and lots of 1 morphisms and 2 morphisms and so on between them. And if I take the endomorphisms of the unit in such a guy, I get a braided monoidal n-1 category, and so on. I get down and down and down and down, and you repeat this until you get down to a something something one category. And if you started high enough, this will be symmetric monoidal, and you just see these lines there. Okay, so this is what this is in that case. And for a sigma model plus its Neumann boundary theory for a space X, if you work out what this is as a vector space, or as a category, I told you what it is. It's just a linearization, or it will be, I didn't tell you what it is, but it's just a linearization of the category of functors from maps. Sort of it's a linear, let's say linearization. So linearization, for example, means you take functors of this category into vector spaces. But the relevant thing is that it's functors, or let's say maps from the disk d-1 to X. But the point is that the disk is contractible, so this space is just the same as X. And so it's just a linearization of X. And as I said, linearization means you just, take functors from X into Vec. And what you find then is, oh, this is just a category of representations on the fundamental groupoid. Because, X might be a higher space, but Vec is just one category, so it will just factor through functors from pi1 of X, pi smaller equal to 1 of X. So this is true as a category. And then you have to do some work, not that much, but you have to do a little work to show that this is even an equivalence as a symmetric monoidal category. So that the symmetric monoidal structure defined by the pair of pans agrees with the symmetric monoidal structure on the representation category. Okay. And so great. So for a sigma model, we know that this knows information about the fundamental groupoid. And let's think about how you can recover the fundamental groupoid sort of in general. And the idea that comes in is a theorem of Deligne, which says that or sort of a consequence of a theorem of Deligne, if Q is a compact and superlinear quantum field theory, what this then means, this implies, is that Q of dd-1 will be a symmetric monoidal super multifusion category, for those of you familiar with the terminology. And symmetric monoidal super multifusion categories are classified by or are always equivalent to functors from some finite one groupoid to super vector spaces. Okay, and so you can always recover this finite one groupoid and record it. So as long as my TFT is very nice, is defined in all manifolds and is super linear, then I do have a canonical one groupoid there. In particular, every just linear TFT is super linear, of course. Just factors through vector spaces. So this is good. So if you care about fusion higher categories, there you go. This is your finite groupoid you extract. If you do care about more general things, let me just make the point that this is essentially the Tanakh, the algebraic geometry philosophy. Right, in algebraic geometry, if I have functions on a finite set, that's a commutative algebra from which you can recover the finite set. If you have an arbitrary commutative algebra, you still want to think of it as functions on something. And the something you think of then as an affine algebraic variety. And you can go and define affine algebraic varieties as, or affine schemes even, as the opposite of the category of commutative algebra. So you pretend every commutative algebra has an underlying fuzzy set-like structure behind it. And similar here, if I have any symmetric monoidal linear category, you can go and pretend this is functions on some algebraic or make-believe one groupoid. And so what you should think is that even if you don't have these conditions, even if you're sort of not finite enough to actually throw out a finite one groupoid, you should still think of this as producing for you some make-believe, some fake or affine one groupoid object. Okay. But this is, of course, words and philosophy, and this is very concrete in the multifusion setting. And so even without this compactness conditions, you still sort of pretend that this fundamental groupoid is something like spec of the symmetric monoidal category, even if this is just words and not a mathematical thing. Okay. Right. Questions?
Go ahead.
Okay. So far, sort of so unspectacular. I think those of you who know Deline's theorem, this is the thing that should come to mind if you do these sort of questions. You sort of first identify all symmetric monoidal categories that hang around anywhere. You use that they look like representations of a groupoid or of a group, and then you try to do something with that, right? Usually you then de-equivariantize and do things like that. So this is sort of a very familiar sort of instinct you should have in quantum symmetries and quantum algebra. But now the sort of key is that we also identify the higher homotopy groups. And this works as follows. So as I said earlier, classically, pi k of x is an abelian group of an action by this fundamental groupoid. And I said, when I say this, what I really mean is a functor or local system. So this is an object inside rep pi. So this is functors from pi smaller equal to 1x to abelian groups. And now, okay, fine. So you have this category. And you can ask, can I sort of just categorically characterize what such abelian group objects in this, so which is a, this is a functor like this, which amounts to the same as an abelian group object in the category of representations, in the category of just functors from pi 1 smaller equal to x to vector spaces. So the data is, let me sort of reverse the data of a local system on pi smaller equal to 1x, so a functor from pi smaller equal to 1x to abelian groups is the same data as a commutative and co-commutative Hopf algebra in the category of functors from pi smaller equal to 1x to finite dimensional vector spaces. So this is if pi smaller equal to 1x is trivial, this is something familiar. If you have a commutative and co-commutative Hopf algebra in the category of finite dimensional vector spaces, that's the same data as an abelian group and as a finite abelian group. And if you sort of look at the category of representations of some groupoid, you will find that this again is a functor from the fundamental group or two finite abelian groups. So it will be a family of finite abelian groups. Okay. But that's great because you do understand this like we have a way to extract this category from our TQFT, namely it's QD of D minus 1. So what we should be looking for is commutative and co-commutative Hopf algebras in here, right? If I sort of geometrically can identify commutative and co-commutative Hopf algebras in this category, then this will produce for me abelian groups with local systems. And the catch is that from just the axioms of a TFT, you can find a sort of family of interesting Hopf algebras in here. And this is what we do next. And again, some of these constructions will be sort of the algebraic variants. I won't get to these very much, the algebraic variants, but they will sort of, if you unravel everything, they will look familiar in the setting of fusion and braided fusion categories. Okay, so here's what these Hopf algebras are.
Can I ask a question?
Yes. Yes.
Yeah. Would this be possible that we can just generalize this to the multi-fusion category and with target vector space category is modified in some multi-fusion version of the vector space category?
I see. So you mean you could ask what are commutative and co-commutative Hopf algebras in some specific multi-fusion category?
Yeah.
Yes, you can answer this question. The way I would do it is to use, maybe there's a direct proof, but one proof is you first classify symmetric multi-fusion categories. They are of the form, if you're superlinear at least, they are of the form functors from some finite groupoid to super vector spaces. And so then you are back in a version of this example. And then you again have to classify commutative and co-commutative Hopf algebras in here. And now again, they will be abelian groups with a local system. And I guess if you're in just vector spaces, if it's a symmetric multi-fusion category without super, it will be sort of abelian supergroups with some compatible action. So this is what you'll get out. I think if you start with a braided fusion category, if you don't have symmetric, then these will just be commutative and co-commutative Hopf algebras in this braided category. And I think there's not much. I think it depends on the braided fusion category in that case, what they are classified by. I think that there isn't a sort of classification in terms of classical data. But once you're in the symmetric multi-fusion world, it works, but just reducing it back to the vector setting. Just using that every symmetric multi-fusion category already looks more or less like this. Yeah.
Okay, thank you.
You're welcome. And that's in a way that's the key idea here, right? This is just some symmetric multi-fusion category if I start with a TFT. But the point is I then use the Leon's theorem to say, look, this is representations of a group. And then if once I've managed to build Hopf algebras in the symmetric multi-fusion category, I do know that they will actually correspond to abelian groups with an action. So that's always sort of algebraically, so geometrically from a TFT, this would just tell me, oh, this is a symmetric multi-fusion category. And then I use my algebraic machinery to say, but this means I can extract a finite group. And then the TFT will tell you, look, here's the system of just commutative and co-commutative Hopf algebras in the symmetric category. But then again, I use algebraic machinery to tell me, but these are exactly the same as the data of a finite abelian group with an action. So I'll explain the geometric side now, why you get these Hopf algebras. And what these Hopf algebras are essentially, they're sort of a slight fix, but let's sort of start looking at just the solid torus of dimension D. Or sort of these solid K, variants of tori of dimension D. So these manifolds, Sk cross D, D minus K. So for example, if D is 2 and K is 1, this is an S1 cross a D1, so this is a solid annulus. And if the dimension D is 3 and K is 1, this is an S1 cross a D2, so this is a solid torus, a solid donut, and so on. Okay, so these are interesting manifolds. These are open D-dimensional manifolds, or D-dimensional manifolds with boundary. So my TFT will assign a vector space to these manifolds, right? It's an open-closed TFT. It knows what to do with a manifold with boundary, and it will give you a vector space. But I don't just want to get a vector space or a super vector space. I want to get an object in this category. So I have to, rather than looking at morphisms which go sort of from empty to empty in the Borderson category, I want to look at morphisms which go from empty to the disk of one dimension below. So in this case, I want to look at a morphism which goes from empty to an interval. And the way to achieve this is to just sort of take these donuts and take a bite. So I'm just sort of taking out a bite of these donuts. So this is like an actual donut. Take a bite. And this now I can interpret as one of these open-closed Bordersons from empty to a one disk. Right, so this is sort of the outgoing boundary that's sort of relevant for the categorical direction along which I can compose. And this is the boundary where I impose my boundary condition. And same here. And this I can do in all dimensions. And this gives me a morphism in the Borderson category from empty to this disk of one dimension lower. Okay, so this is a three-dimensional manifold with two-dimensional boundary, and it's a three-dimensional Borderson with two-dimensional boundary, open boundary that goes from empty to a two-disk. Okay. Questions on these pictures? Okay, and it turns out, and therefore, just if I apply my QFT, my TQFT to it, this gives me a morphism from, back to this symmetric multi-fusion category. And so in particular, it gives me an object of the symmetric multi-fusion category. And it turns out, and this is the first theorem in this project, that these are Hopf algebra objects in this category. And the multiplication, just to give you sort of a rough idea how these Hopf algebra objects look like, those are sort of morally a sphere across a disk. And so the multiplication just uses the pair of pans on the sphere, and it just sort of compactifies or crosses with a disk to make it into the correct dimension. And then you have to sort of make everything compatible with the byte. Sort of you have a byte cross interval, which is sort of tracks along, or is compatible with the multiplication in this, right? Because you really want to say there's a map from H tensor H to H, where tensor means the multiplication in here. And so you have to sort of set this up correctly that it works with the byte. But morally, it's that. And the co-multiplication morally is you just use the pair of pan structure on the disk. And I should say what's quite subtle is that we really want to work in a framed setting. So we don't want to have oriented structures. We don't want to have pivotal structures and all the like. We just want to have sort of plain higher fusion categories. And therefore, we have to be quite careful how to frame this guy compatible with this byte and why this multiplication and co-multiplication are framed and so on. So just as an example, you could wonder, there seems to be another multiplication, which is you take the sphere and then you take the pair of pans, but sort of read the other way around. And similar here, there seems to be yet another co-multiplication, which is this co-pair of pans times the disk. But both of these will be disallowed by the framing. And in fact, there is no way to arrange a framing to allow you a multiplication of this sort and a multiplication of this sort. So you always have to, one of them has to be a multiplication, the other one has to be a co-multiplication. So, which is quite interesting, which really tells you that sort of the framings move closer to just generic Hopf algebras rather than sort of very particular one where, you can dualize things a lot. Fine. So these are Hopf algebras in this category or in this category D minus 1. And if k is large enough, namely k is larger than or equal to 2, right? I told you the multiplication is a pair of pans. Where did I cheat? I might have cheated because the pair of that's right. If k has to be larger or equal to 2 to make sure that this Hopf algebra is co-commutative, because if k is equal to 1, then here you would have the d minus 1. And I think this wouldn't be compatible with the byte structure anymore. So maybe I have the case wrong here. But at least sort of, okay. The thing I think we can all agree on is that k has to be large enough to make sure that the pair of pans is commutative. I would have said k has to be larger or equal to 1 because S1 is already a commutative algebra. But maybe I have some framing issues here, or maybe I just had the case wrong in the slide. I have to look this back up later. On the other end, it's clearer k has to be smaller or equal to d minus 2. If k is equal to d minus 1, you get here a d minus 1, which is a 1. And clearly d1, that's not a commutative algebra. That's just an algebra to one disk, right? This one. Okay. So point being that if k is large enough away from the boundaries, this will be commutative and co-commutative. Just again by the usual arguments, the usual sort of EN arguments. Okay. Right. And now you can go and try to compute these Hopf algebras. And the first example you should do, just to sanity check what we're doing, is to compute these 4 sigma models. So suppose I have a sigma model coming from a space and its sort of canonical boundary. I told you that this symmetric nodal category is representations on the fundamental groupoid. And now you can go and try to compute the value of this guy. And again, as an object in this category, it's fairly straightforward. You just write down the formulas and you find this is precisely the linearization of the group algebra of pi kx. Sorry, the linearization of pi kx, of the set pi kx as an object. And then the interesting part of the computation is to check that actually this multiplication and co-multiplication, the co-multiplication sort of tells you how you should think of this vector space as coming from a set, what are sort of the copyable elements or the group-like elements, and the multiplication tells you the group structure. And so you really recover the group algebra here. Great. And so therefore, by this correspondence, you do recover the group itself. And that's great. And so you go and generalize that. So I have a way from a sigma model to recover the higher homotopy groups as a local system. And so I just use this as a definition. If my k's are in the correct range, I define pi k of q to be just the value of my TFT on this torus minus a byte and seen as a co-commutative and commutative Hopf algebra in q dd minus 1. And if q is nice enough so that this category is a symmetric multi-fusion category, so this is implied if this is compact and superlinear, then this data is equivalent to a finite abelian group with an action by this fundamental group. Okay, and there you go. These are, if you want, the higher abelian homotopy groups of one of these QFTs. Are there questions at this point? So I will talk a little bit about how they look like for higher fusion categories.
Okay, I have a small question.
Yes.
So you talked about commutative and co-commutative of algebra, generalize abelian groups. So in which case, commutative and co-commutative of algebra are not abelian groups? Right?
Okay, so the point is that you have to be so let me say it like this. So a concrete example is you can look at one of these exotic symmetric tensor categories like Reutter and these gadgets, where these don't have to look like an abelian group. There's usually in a commutative and co-commutative Hopf algebra, you also have a part which looks like a Lie, which looks like the Hopf algebra of a Lie algebra that you get. And these would appear even in the symmetric multifusion categories and finite characteristic. You tend to see these things coming up. Roughly the idea is that the thing which makes these finite abelian groups is that if you have a commutative and co-commutative Hopf algebra in vector spaces or super vector spaces in characteristic 0, in finite dimensional vector spaces or super vector space in characteristic 0, what will happen is that they will automatically be semi-simple algebras. And that's what makes them that's what gives them a sort of set structure which looks like a linearization of a set. Right, this makes them, for example, a commutative algebra, and if the commutative algebra is semi-simple, then you go, I know semi-simple commutative algebras, those are just functions on a set, and that gives you the underlying set of the abelian group. And once you're there, you're sort of good to go. So you have to have some machinery which makes these semi-simple for free. And in finite characteristic, in characteristic 0, this essentially works because there is sort of a separability idempotent construction like you can do, which works once you can invert the dimension of the Hopf algebra. So once you can invert the dimension, you can sort of write down a separability idempotent, making these really separable algebras. And so you already see that in finite characteristic, this won't work. So if the dimension of the Hopf algebra is sort of, divisible by the characteristic of the field, then I think things become more subtle. And if I understand it correctly, you do have examples of things that come from variants of Lie algebras that are commutative and co-commutative and finite characteristic. So sort of a bit subtle, right? You have some machinery that gives you semi-simplicity for free in characteristic 0 that allows you to make this statement. Yes.
Thank you.
You're welcome. Okay. But fine, if we work with the complex numbers as we do here, and just say we work in super vector spaces and the higher variance of these, then all is good and fine, and you just extract your finite abelian groups. And of course, this only works if my ambient category was symmetric. If I'm in lower dimensions, this will be, for example, a braided monoidal category, and this object will just be a commutative and co-commutative Hopf algebra in that braided monoidal category. And there's nothing more you can say. And if you're even less in a less dimension, if this is just a monoidal one category, then this won't be a Hopf algebra because I can't even define what a Hopf algebra is in a monoidal category. But if you work a little harder, this will recover a Hopf monad and on that monoidal category. But I won't go into this. Okay, just a few examples. Let me just sort of work this out for higher fusion categories. And for this, let me now sort of in the last 5 minutes of the talk actually briefly say what very sort of sketchily sketch what the definition of a higher fusion category is, just so that we have the terminology. If you don't care about these, you can just ignore me for the slide, and then the next slide is maybe again interesting. A fusion n category is just a complex linear monoidal weak monoidal n category, which has the following properties. It's additive and higher idempotent complete at all levels. These are just sort of Karoubi completeness notions that you also know from fusion 1 categories, and there's sort of correct higher categorical analogs of these. So you can sort of take direct sums, and this is sort of a construction, a sort of lax higher version of idempotence that you need to allow to split. Moreover, again, this is sort of a very finite gadget, so this should have duals and adjoints at all levels. So all objects have duals on both sides, and all one-morphisms have adjoints, and so on all the way, also very familiar. And then another condition that you ask is if I have any n-1 morphism between any two n-2 morphisms, then I can look at the algebra of endomorphisms of that. Right? If you think of it in higher string diagrams, n-1 morphism is something which looks like a line defect that's thrown on some higher sheets of some form. And this algebra of endomorphisms is the algebra of point defects that live on that line. And these algebras you ask to be finite semi-simple. So that's sort of your condition. For example, this is already satisfied if your category is at the top a C star category. If all the, if the sort of one categories of top morphisms form a C star category, then these will, for example, be finite semi-simple. If it forms a finite dimensional, a C star category with finite dimensional Hopf spaces. And then there's a fourth condition, which I'll get to in a second. You can sort of unravel this for one. C linear monoidal 1 category is additive and idempotent complete. It has duals. And for all, right, zero morphisms, i.e. for all objects X, the endomorphism algebra of that object is finite semi-simple. So this already starts to look like a multi-fusion category. That's not quite there yet. Okay, I should also say multi-fusion, by the way, and didn't impose the fusion condition. The condition that's missing is that you only have finitely many simple objects. So once you have that, then this would be a multi-fusion category. And this would be sort of the analog here. I'll say in a second how to phrase this. But right, to even say this, I briefly have to say what it means for an object to be simple. An object X is simple if and only if it's indecomposable. That's a theorem and not a definition, but fine. Sort of once you know it, you can take that as your definition of simple. If and only if I take the identity on X and the higher identity, and then look at the endomorphism, sort of the point where I get a vector space out. This has to be one-dimensional. Right, again, for n equals 1, this is just saying that the algebra of endomorphisms of X is one-dimensional. And you can think of this X as some higher surface or sort of d-dimensional object, and the endomorphisms of the identity, blah, 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 blah. It's just sort of the points that live in that object labeled X. Okay, and it then turns out that if you do this computation, I said pi k of C, at least if C is sort of a fusion 3 category or higher, pi k of C will be an abelian group with an action by pi smaller or equal to 1 of C. So you can take this quotient, you can take this abelian group and quotient out by this action. This will just be a set. Who is this set? The set turns out to be the simple objects in omega n minus k C. So omega means you take the endomorphism of the unit and you go down. So this is the n minus k morphisms that are the simple n minus k morphisms that just go from the unit to the unit up to non-zero morphisms between them. That turns out to be an equivalence relation. You can take this quotient. So if you sort of think of it physically, it's the k-dimensional simple defects that live in a boundary theory up to domain walls. So these groups classify defects up to domain walls, not up to equivalence, but up to domain walls, really. And this sort of captures these. And this you should really think of this as this the information here. And in fact, it turns out this is also the finiteness condition. The finiteness condition is you ask that simple k morphisms up to non-zero morphisms, those form a finite set, right? And let me maybe say briefly that if n is equal to 1 and k is equal to 0, then what this is just simple objects if n is equal to 1, I should say this way, and k is equal to 1. Yeah, this way. Then this is just C itself, right? This is omega 0 of C, which is C. And then what you have here is simples in C up to non-zero morphisms. But by Schur's lemma, this is the same as simples in C up to isomorphism. And so what this captures is pi 1 of C, if you like, up to this action in a fusion 1 category is precisely the simple objects up to iso. So it's but again, I should say for n equals k equals 1, you don't have these groups. Right? For example, if the final group is trivial, if I look at sort of higher vector spaces or super vector spaces, if I have d variantized, get something like this, I would find that the simples in this sort of the simple n minus k dimensional defects up to non-zero morphism, this inherits a group structure. This would just be equal to pi k of C and would therefore be an abelian group. which is very cool, which tells you that sort of these higher fusion categories, if you assume that there are no lines around, which you can, for example, again achieve after equivalentization, de-equivalentization, then you learn that there are no interest, there's sort of the fusion rules are just groups. And in general, if I take this quotient, right, this is an abelian group quotiented by some group acting on it, this will be a hypergroup. And in fact, this here always in all dimensions has a hypergroup structure, and this just sort of is a theorem telling you that this hypergroup structure, which you have sort of canonically on here, agrees with the one which is given by take this abelian group and quotient by this group. And what the hypergroup structure, if you like hypergroups or no hypergroups, what this is in general, it's some hypergroup, and it recovers, it actually now recovers for n equals k equals 1 the fusion ring. So these guys are sort of the higher analog of fusion rings. You have them in all dimensions for all dimensional operators. And the fusion ring structure is now just this quotient of groups, this abelian group by this finite group. And that's very cool. So this gives you some information of how the higher fusion rings will have to look like. And let me sort of just end with a bit of an outlook and some applications, why we do this, why we develop this stuff. Originally, we wanted to develop this to understand S matrices of modular fusion 2 categories and higher modular fusion categories. And this works sort of in this generality. And you can prove a lot of things about it in this generality, which is very useful. For example, in this generality, there's a pairing between pi k of q and pi d minus k of q. And this pairing is trivial if q comes from a classical space. But if q comes from a higher fusion category, for example, or some more interesting examples, it's very much non-trivial. So you sort of see that there are lots of examples which do not arise from topological spaces. And for example, if q is a higher fusion symmetry, what Sk is precisely the S matrix. It's given by Hopf linking k-dimensional with d minus k-dimensional operators. So again, for braided fusion 1 category, it looks like this, and in higher dimensions, it's just you have to sort of Hopf link the right pairing of dimensions where you can form a Hopf link. And here's an interesting thing you could look at for topological spaces or abelian groups, the sort of homotopy groups of topological spaces. A priori, the homotopy groups of topological space are not that interesting. They're just abelian groups. They become interesting or computable because they're things like the Poupon exact sequence, which tells you if I have any map of topological spaces, I have a long exact sequence which goes pi kx, pi ky, and then you have pi k of the homotopy fiber of f, pi k plus 1y, pi k plus n, 1x. And these are sort of the tools that allow you to actually compute homotopy groups. And it turns out that we build a generalization of this long exact sequence for any map of quantum spaces, if you interpret map of quantum spaces correctly, for any of these TGFTs with boundary theories. And then it turns out that these SK, they do indeed appear as certain connecting maps in a certain non-classical instance of this Puppe sequence. And this allows us to prove, and this is sort of the reason we started this whole project, this allows us to prove that the bike theory of a quantum space, so the big theory is an invertible theory, if and only if these matrices are non-degenerate. So they're square and non-invertible matrices. And this is really right. This is sort of the SK appear as some connecting map. So if this connecting map is an ISO, this means that sort of the group that's off a level is the zero group. And that being the zero group will be sort of easily seen to be equivalent that the bike theory is invertible. So this is saying something like if you have one of these quantum spaces, TGFTs with boundary theory, then the boundary operators braiding non-degenerately will be equivalent to the bike theory being invertible, which, if you like physics, is the same as saying the bike theory has no defects which live in the bike theory. And if you like mathematics, if your thing comes from a higher fusion category, this statement is saying that the higher fusion category is Morita invertible. And if the higher fusion category comes from a braided fusion n-1 category, then this is again equivalent to saying that B is width invertible. It's sort of invertible up to centers. And so this is sort of a key theorem for braided fusion 1 categories already, which at this point I think is not, well, for fusion categories it is proven, but it's already very hard that a braided fusion 1 category is modular, or sort of the generalization of modular, namely this pairing is invertible, if and only if it's invertible up to width equivalence. So these are sort of technically fairly tricky to do, and this gives you a TGFT reason for this statement to be true. And it works in higher dimensions now. And so the point I want to make really is that this is a tricky condition. This being Morita invertible is very hard to check, right? It forces you to look at some higher category of some 4 or 5 or whatnot category of these higher categories and check invertibility there. Whereas this condition is fairly easy to check. This is just asking that, or at least sort of very much low categorical. It's just asking that certain matrices are invertible. And this relates these two. And then just for modular 1 categories, you immediately from a statement like this, you get sort of very cool things like the Linde formulas, which relate the S matrices with the fusion rules and these hypergroup structures and so on for these higher modular fusion categories. So you get a good handle on these categories. Right. That's the end of my talk. I hope you enjoyed it, and I'm looking forward to the questions. Thank you.
Okay, so I have a question. Okay, so my question is, so for topological space, the homotopy groups are the spaces of maps from sphere to the space modulo the homotopy.
Yes.
Then for the quantum homotopy groups and quantum spaces, what are the quantum spheres?
Yeah. Let's see. So so you ask, I interpret there's an easy interpretation of your question and a harder interpretation of your question. Let me start with the easy interpretation of your question. So you see, so this is how it sort of so if you look at sigma models, right? Then I said what these algebras are. Let me sort of ignore this byte issue. No, let me first ignore this byte issue. If I ignore the byte, what the vector space is I assign to this is essentially just maps from Sk cross a disk d minus k into X, into my target. And the disk is contractible, and so this is the same as just maps from Sk into X. And so this is sort of morally why you recover the homotopy groups, right? I should say a little bit more. It's not quite that it's maps. What you really have to look at is pointed maps. But this is achieved by this byte. Because the byte is saying, you have to sort of, everything has to work relative to this, and this is sort of where you put the base point of the sphere. So from that perspective, you could say, what sort of, where the spheres come in is that you evaluate your TFTs on these things. And I want to get vector spaces out, so I can only evaluate it on D manifolds. And so I have to take my K sphere and make it into a D manifold. And how do you do it? You just cross with a disk, and then it's top dimensional. So this is sort of a one sphere, but from the perspective of a 3-dimensional or 4-dimensional bike theory, looks like that. And this is the base point is this disk, right? So you really see the spheres in the base point, and this is what gives sort of that structure. And the point is that somehow the abelian group structure on the homotopy groups arises from a certain structure on spheres, on some co-group structure on spheres, on pointed spheres. And this co-group structure on pointed spheres lifts to these Bodison categories. So if it's all compatible with this thickening, this makes this all still work. And so that's sort of the first answer, is that you can just sort of lift these spheres to d-dimensional objects in the Bodison category. And you can even lift the sphere as a pointed object to this minus a byte. And all the structure on the sphere that gives rise to the fact that maps out of it are groups already lifts the structure here. So that's one answer to your question. This is where you see the spheres. Another way to interpret your question is to really say, okay, let's like really take the perspective that a space is a quantum field theory, or is a quantum field theory with a boundary theory. Now you could ask, can I sort of describe these, for example, as sigma models with target Sk? This should be sort of a sigma model with target Sk is morally what the sphere then is under this correspondence. Can I describe these groups as being related to maps between sigma models where you use the target Sk and my other thing?
Yeah,
and there I
that's
don't.
my question. Yes.
And that question, I don't know the answer. The first problem I would point out, and this is a problem I keep running into in various projects, is that this correspondence really only works cleanly for pi finite spaces, so spaces where all the homotopy groups are finite, and there are only finitely many of these. That's where you really have TQFTs. And the point is that the spheres are not pi-finite spaces, right? The spheres have, the n sphere has pi n, which is a set, and then it has infinitely many homotopy groups that are non-zero. And so it's just not a pi-finite space. So I can't turn it into a TQFT. I can't define a sigma model with target the sphere, which is a TQFT, sort of one of these homotopical things. And that makes it sort of, that makes the question in a way a priori ill-defined. The sphere is just not a thing. But you could now argue, can I sort of enlarge this sort of, the question you should then ask is, okay, if pi-finite spaces correspond to, at least with some truncatedness condition, correspond to TQFTs with boundary theories, what are then general spaces, right? And then maybe you should say those correspond to more general QFTs. Like not, I mean, if I have a sigma model, it's really a manifold with some Riemannian structure would be your space. But maybe there's sort of an in-between thing where you can do something slightly homotopical or not. But I'm not sure. There's a variety of questions like this where you could ask, oh, if I present my space using a CW complex, say, how does that translate into the TFT language? Another question also along these lines is, you could say, okay, fine, I can recover the fundamental group and the higher homotopy groups. If I want to get back to space, what I need to sort of understand is also the K invariance, the way how these groups glue together. Is there a way to extract that from the TQFT? And there I'm also not sure.
Okay.
I can say a little bit about this, but I first want to hear other questions. You can just remind me later, and I might come back to this.
Wait, so your base fields are complex numbers or not necessarily?
Algebraically closed characteristic 0.
Characteristic 0. Okay.
That's what I need. So it's really, I mean, so for this statement here,
Yes.
I don't need, so in this generality, I don't need anything. Even my target can just be any symmetric monoidal 2 category, right? I don't need any field whatsoever. But this would just give me out, so this is just a statement that this is a symmetric monoidal object and these are Hopf algebras. So this is just geometric that these are Hopf algebras. And you could call the Hopf algebras the homotopy groups, and I think that's in sort of weird characteristic, for example, that's just the thing you should do. But then to really extract actual groups, then you have to work in algebraically closed characteristic 0.
Yes. That's actually what I want to ask. So if say for the Hopf algebra objects that you look at, so even if we're not working over algebraically closed category 0, we still get Hopf algebras, right?
Yes.
So do you know? Let me formulate the question. So do you know if we have some Hopf algebra object in the suitable symmetric tensor category, then you can define something called Cooper-Berg invariant for 3 manifolds?
Yes.
So well, in over C, let's say algebraically closed category 0, you can get two interesting things. But I think probably over characteristic P, right? If you consider this interesting Hopf algebras, maybe they can give us some interesting three-dimensional three manifold invariants. So do you have some intuition? So how does the 3 come? So because you're looking at d-dimensional TFTs, right? And
that's
so
right.
Why is there 3 somehow lurking around?
Yeah, so what I can what I can say is the following. So let's suppose you try to do this in finite characteristic, then if you want to build a TQFT that's defined on all layers, you could start again with a braided fusion one characteristic, one category in finite characteristic, for example, and try to build a TFT with boundary theory that's defined in 3 and 4 dimensions. What you would then run into, or an issue that would come up, is that you would have to ask this braided fusion category to be separable, meaning that the global dimension is non-zero. That would be imposed by asking that the TFT is really defined on all borders. And that's what I believe. And this would force things like the Müger center of my TFT to actually also be a symmetric multi-fusion separable category. And this would again force it, even in characteristic P, into super vector spaces. Because sort of even in characteristic P, a symmetric multi-fusion category, which is separable where the global dimension is non-zero, is representations of some fundamental groupoid in super vector spaces. And so you, if you want to move to, for example, the Kuperbeck invariant and the variety of invariant, Lubashenko invariant, and so on, in finite characteristic, these are non-semi-simple theories.
Right.
These are really built, say, from Hopf algebras in heavily non-semi-simple categories. And you do get still invariants out, but if you try to make these invariants into TQFTs with sort of, there's a 4D bulk theory still and a 3D boundary theory. But if you look into these examples, what will happen is, I think the 4D theory, I mean, this is now just what I believe, is that the 4D theory is actually fully defined as a 4D theory. But the 3D boundary theory, the thing which sort of generalizes Reshetik and Turayev, that is not defined on all 3 manifolds. And this is where this not necessarily compact comes in. So I believe that you do get a not compact 3/4 theory out of say these Kuperbeck invariants, or out of a non-semi-simple, a braided finite tensor category with a modified trace. You do get a non-compact 3/4 theory, and meaning it's just not defined on all top dimensional borders. And part of sort of the work we're doing here is really take care that these invariants and constructions are still defined for these not necessarily compact things. So if you look at sort of all the formulas we write down everywhere in terms of borders, we just have to make sure that there's always a non-empty outgoing boundary. And I think that's true. And so if you believe these statements, that things like the Kuperbeck invariants and so on, that they are non-compact TFTs in this sense, then they do give you these Hopf algebras in very symmetric and braided categories.
I see.
And in particular, in that dimension, in dimension d equals 3, and the bulk theory being 4, you would get, right, this is the d equals 3 case that you care about. You would get the 2-sphere, and the 2-sphere would just be a braided monoidal category. And what this means is that in these 3/4, at this 3/4 level you care about, you would get a Hopf algebra in a braided monoidal category. And what I believe this Hopf algebra will be is the universal coend in your underlying modular finite tensor category. That sort of construction. If you know about these non-simple TFTs, that's what
that is probably that corresponds to 1 puncture torus. That's Hopf algebra.
Right, exactly. And this is the 1 puncture. That's right.
Yes,
exactly.
yes. Okay.
The other ones would be less interesting. Like they would sort of degenerate fairly quickly in this dimension.
I see.
Right, the other one
Can you
looks
remind
like
us the antipode of this Hopf algebras?
the antipode is
Topologically.
Yeah.
Topologically.
Let me remind myself. The antipode is funny. It is if I'm just looking at the boundary theory, so if let's sort of ignore the bulk, this is just another sphere. And if I also ignore the byte, it is what's it doing? I can only do it for S0 times S0, sorry. For S0 times S0. And then I do it for S0 times S0, and then that allows us to figure out what it is in general. For 0 times S0, the antipode looks like a quarter rotation. So you take your square, I mean, it's just 4 corners, or maybe whatever, right? I mean, it's really a D1 times D1. This construction more generally would work for D1 times D1. And then it's the square, and what you do is you quarter rotate the square. That's what the antipode is. And in higher dimensions, there's sort of corresponding analogs of this. It's always just it turns out to always just be a diffeomorphism, but it's a diffeomorphism that sort of heavily twists around the framing. So that's what it is, but I have to look it back up, what it actually was. This will be part of the paper eventually. But this is how you should think of this.
Yeah. Okay, thanks.
You're welcome. Yeah, it's
Another question. Do you have something else to say?
Yeah, I just wanted to sort of a question that sort of almost came up, or that roughly came up, is and a question I find quite nice, is the question, if you do have, so if I have a high dimensional d-dimensional quantum space, you know, and I can extract this finite groupoid and these finite abelian groups, how far away is this from a topological space? So are these indeed the underlying groupoid and finite abelian groups of a topological space? You could ask, right? Is this just a shadow of us? We could have actually recovered a topological space, but we didn't. We just recovered these groups. Is that what's happening here? And the answer is, I expect no. And what will happen, namely, is this is what I was saying earlier. There's sort of this information of how these groups are supposed to glue together in a topological space. In a topological space, you have so-called k-invariants, which are certain cohomology classes on these spaces, on these groups with respect to some of these other groups, and some obstruction theory to build these together. And if you work with fully extended TFTs and everything is as nice as possible, if you try to glue these spaces back together to build myself Q, if I try, these abelian groups back together to build Q, then the sort of cohomology in which these k-invariants are supposed to be valued is not only group cohomology, but is some sort of more exotic cohomology theory, which uses knowledge of modular tensor categories and things like this. So there's sort of, out of these spaces of TFTs, there do arise interesting cohomology theories which contain knowledge about modular fusion categories and these things. And in that cohomology information, that's still exotic. So if you have a higher fusion category, you could ask, oh, is this just saying that this is just a non-exotic object? I'd say it's still exotic, but the exoticness is not anymore in the fusion rules. These are sort of boring. I mean, these are just groups. But the exoticness is in the way they fit together. And the way they fit together still knows, in the sort of right degrees, still knows about braided fusion categories and things like this. So it's quite interesting how this sort of, in dimensions 3 and 2, where you have braided fusion categories and fusion categories, you have these sort of massively exciting fusion rules. And suddenly in higher dimensions, you have, you know, it's sort of more subtle cohomological information that still knows about these interesting things. So the source of the exoticness is always modular tensor categories and fusion categories. That's where the exoticness comes from. But where you later in higher dimensions see the exoticness is not in the fusion rules anymore, but it's in some sort of deeper connecting information. That's what I wanted to say as sort of an extension of a previous answer.
Thank you again.
Thank you. One more thing I want to say, sorry. I think a better answer to the question earlier about what's the antipode. If I have sphere times disk, what you do is, formally geometrically, I think it is just, the antipode, I think, is just the product of the antipodal, fun coincidence, maps on the sphere and the disk. So you do sort of the orientation reversing map on the sphere and on the disk. And the Cartesian product of these is orientation preserving. And that's what the antipode is if you would be in an oriented setting. But since you're in a frame setting, you have to sort of even do more. You do these two antipodal maps, and then you have to adjust the framing back to make it sort of all work. And if you do work it out for disk D1 times D1 geometrically, what this is doing, this sort of flipping both directions and then fixing the framing, this is the same as this 90-degree rotation, right? Sort of flip this way, flip that way is a rotation.
I see.
And in general, that's what it is. It's antipodal here,
yeah.
and careful framing, fixing.
Okay.
Yeah. And I think in
Yeah.
algebraic settings, the interesting algebraic information is often more in the framing adjustment that this is actually a framed map.
Okay. I see.
Yeah. Yeah, I've never noticed that these maps are called the antipodal map, and this is the antipode, which is fun.
Yeah, that's very good.
I will stop the recording now.